This is section 1.2 of Math 1's notes. Today we're going to interpret scale and origin in graphs and data displays. So really what we're going to be doing here is we're going to be looking at some graphs and we're just kind of going to be describing what's going on in them. And then later on we're going to go the opposite direction where we have to draw the graph for what's described for us in words. So let's take a look at this first graph and let's kind of just talk about what's going on here. The first thing we want to notice is what we're actually talking about or what we're comparing here. So we're actually looking at time compared to distance. So when we look at that, we want to notice that as time goes by, you can notice this direction, as time goes by this way, then the distance is also changing. So here we go a little bit amount of time, but we have a huge amount of distance that we changed. It went very quick, the distance did. Here, although time is going past, no distance is moving, which means that we've probably stopped at that point. So I'm going to call that a stop on my graph. I think that that's where I've stopped at. And then again here, as time continues to go by, here we are moving fast again. So I'm going to put that we're moving fast. So we were moving fast, or we went a quick amount of distance is really what it is. So distance went far, we stopped, and then we went a large amount of distance again. So I'm going to say that we were moving fast, which meant that we went far. So we really can just describe what's happening on the graphs by looking at the two things that we're comparing on the origins. So we compared time to distance. This next one says describe what's happening in the graph. We're driving to school, and again we're comparing time on this axis to distance on this one. So again, if we're looking at time, very little time goes past, but we go a large distance. Look how steep that is. The steepness of that is going to tell us that we went a large amount of distance fast. So maybe time and distance, that means we went pretty fast, a large amount of distance. Then we probably stopped right here. Then we're increasing our distance very slowly right here. It looks like we stopped here, and again we're kind of increasing at a constant speed again here. So maybe we're going like 30 miles per hour here, just kind of guessing, but we're going that 30 miles per hour the whole time, because if you look at that slope is the same, it's constant, it's a constant slope. But it doesn't move very quickly on the distance. Here, if I were to like describe what was happening, I would maybe say we're going like 60 miles per hour or something. I mean, just guessing. We're clearly going faster here because our distance is really steep on our slope, which means we went a large amount of distance in a short amount of time. So what I've described here is not necessarily what you're going to describe. It can be different than mine. You just have to justify what's happening in the graph according to your knowledge. The next problem here says draw a graph to represent each situation. It says a school bus on its morning route. The first thing we're going to do is distance compared to time. So we're going to draw our axis here. We're going to have time down here. And we're going to go distance on this side. And we're going to draw just a quick graph representation of what might happen on the morning school bus. Well, I think on the morning school bus, we would probably grab some distance. We would travel some distance. Then when we stop, we'd probably travel some distance, maybe not the same amount, and then we'd stop. We'd travel some distance and then stop. So we would repeatedly do that kind of movement. Then it says to compare time and speed. So if we're going time and speed, what would be the difference between those two? I think that it would be pretty similar. I think that when we're doing time compared to speed, I think that on the speed we would not necessarily start out as at a constant necessarily. I think that we might have to show that we're speeding up, meaning we're getting faster and faster, then we would stop. Then we might get faster, 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 and then stop. So I think that on the speed, and maybe we should have showed some when we were stopping. We maybe should have. So here we are accelerating. Here we are stopping. We're slowing down our speed, and then we actual stop. So again, however you can justify your picture, draw it the best you can, kind of explain what you're doing there. So this would be the speeding up part, this would be the slowing down part, this would be the stopping part. Probably my second little idea is better than my first one there. All right, this is a ride on a Ferris wheel. It's going to be height versus time. So we can go time on this, and then height over here. And then again, like I said, you guys, not everybody's is going to be the same. We're just going to do our best that we can here to kind of describe what's going on. I think when we start on a Ferris wheel, the very first thing we're going to do is we're going to be stopped. Like when we get on, we're going to be stopped, which means our height's probably going to start like 2 or 3 feet above the ground here. But we're going to be sitting there for a few minutes. Then we're going to go a little bit higher, and we're going to sit there because we're going to get somebody back out onto the Ferris wheel or off the Ferris wheel. Then I think we're going to go a little bit higher over time, and then we're going to stop again. A little bit higher over time, stop again. So that would be my representation of what I think a ride on a Ferris will be. Then you get going, like finally everybody's boarded and you ride for quite a while. But your height would go up, and then it would come back down. And then it would go up and come back down, like in a kind of like a cyclic function here where it repeats itself up and down. So not always would you just be coming on and off like these would be. You would actually ride the Ferris wheel, and I think that would look more like this, where your height goes up and down, up and down, up and down. So get a nice, good representation of what that graph might look like, and then let's move on. All right, the next one says you drive your car at a constant speed from St. George to Orem. So again, we're going to just draw. I'm still going to use time on my axis. I think that's a good one to do. And then we're comparing speed here, or talking about speed. So we're going to go speed on this side. So we drive our car at a constant speed from St. George to Orem. Well, a constant speed would be the same slope the whole time. So constant, that's really what it means, is the same slope when we're talking about graphs. So my graph representation would look something like this. Now, that's not completely accurate because we still would have to accelerate and then slow down and stuff like that. But because we're only representing what it says here, and it says constant, our slope would be exactly the same the whole time. Okay, on this next problem right here, it says solve the problem. Sarah drove 200 miles away. She took 4 hours to make her trip. What was Sarah's average speed? So 200 miles per hour. I like to always remind myself that I want to find miles per hour, which shows me that my miles are going to be on the top of the fraction. My hours are going to be on the bottom of the fraction. So I'm going 200 miles in 4 hours. When I divide that out, 200 divided by 4, I actually get 50 miles per hour. The question then says, is this answer appropriate? Well, I think it is appropriate that she drove 50 miles per hour. That's an appropriate speed to be going. I think that if we would have done that math and we would have got 100 miles per hour, that's probably not an appropriate answer because you usually don't travel 100 miles per hour. I think if we would have done the math and got 25 miles per hour, I really wouldn't think that you would be traveling 200 miles at 20 miles per hour. So always check your answers and see if you think they're an appropriate number for what we're looking at. All right, last problem here. It says the graph compares distance in meters and time in seconds. What is happening on the graph between 40 and 90 seconds? So here's our seconds down here. You can just barely see that it says time right here and distance right here. Between 40 and 90 seconds. So we're looking at the graph between 40, which is right here, and between 90, which is right here. And it asks what's happening on the graph between 40 and 90 seconds. Well, the graph is right here between 40 and 90 seconds. What's happening there? Well, there's no distance traveled there. We're at 300 the whole time on the distance, which means we have actually stopped right there. We're not traveling any kind of distance there between 40 and 90. And then it says what's happening between 0 and 20. Well, let's look between 0 and 20 here. So here's 0 and here's 20. What's happening between 0 and 20? Well, between 0 and 20, we actually traveled 100 meters. I think it's in meters up here. I can't read what our traveling was, but up here it reminds us that it was meters. We traveled 100 meters in 20 seconds. So that's exactly what we did there. That's what's happening between 0 and 20 is we traveled 100 meters. So again, today we're looking at graphs. We're trying to decide what we think is happening, remembering that ours will not look the same as our neighbor. And as long as we can justify our answer, then we're probably doing the right kind of math here. Thanks for watching, you guys. Good luck on your homework.